Welcome everyone to our session on the health of water where quality matter. And I would like to start to talk a little bit about the global water challenges that we are facing, which kind of coming out through our different presentation, which I'm going to present in a few minutes. So basically, as you probably all aware, our world is becoming more thirsty and we are facing a global water scarcity around the globe, in different places, different magnitude, and different kind of impact on our life, both at home in the US and everywhere, basically. And we are facing really major global water resource challenges, starting with sanitation and access to clean water, which many see it as kind of a basic human right and environmental justice. This is lacking in so many parts of the world. Water and agriculture that really key for food security and safety. We see events that reflect the climate change, that changing what we know about stability of climate. Groundwater, which is the future, is becoming depleted and contaminated severely. There are impact on aquatic ecosystem. Water and energy nexus is a key way. We need water to generate energy and electricity. At the same time, electricity is key for water treatment. And this link is really affected by the water quality. And at the same time, we're facing pollution in sewage, in agriculture, in different parts of the world. And the challenges that we are facing are kind of reflect two major processes. One is long-term overexploitation of water resources that we have witnessed for the last 50 years with increasing global population, increasing quality of life, the changing how much water each of us on our planet are using. And on top of that, global warming has exacerbated the impact of the overexploitation of water, resulting in much frequent and intensive hurricane, drought, floods, and heat waves that affect our life in so many ways. And water quality is maybe somehow being neglected in a way because we are talking about water quantity, but it's really important that we are surrounded by multiple water quality issues. It can started with pathogen in water, which is affecting most people in the developing world, nutrients like nitrate contamination, and issues related to lead and disinfection byproduct that related to the infrastructure of the water supply. On top of that, we're talking about the man-made chemicals that Lee is going to talk about, the PFAS issues, naturally occurring chemicals in the water, which are really becoming a major issues in groundwater resources. Radioactivity in groundwater resources in the Middle East is a major threat for the ability to use groundwater. So altogether, it plays a major challenge. In addition, that water and its quality is the key for ability to generate food. And we are now facing a major shortage of wheat production and exploitation because of the horrific situation in Ukraine. Many countries are going to face a food shortage in a very short future, resulted from the war in Ukraine. And the ability of other sources like the Midwest to address that is really limited given the water shortage, water availability, and the quality of the water in the high plains of the Midwest. About 80% of diseases around the world are associated with water, and we are talking about devastating numbers of 5,000 children would die every day from diarrhea related to water diseases because of untreated water. So this is kind of really a global phenomenon that we are facing, and usually we don't talk much about that. The geogenic contaminants, these are contaminants that exist naturally in groundwater, is all over the globe and really affecting kind of, we call it the silence impact because we don't hear about it. elevated level of arsenic, fluoride. We recently found elevated level of uranium across groundwater in India, which is the largest groundwater exploitation in the world. And these are kind of a chronic impact on the ability to extract clean water and to provide clean water to the population. The energy-water nexus is really a major issue, and through hydraulic fracturing, coal mining, coal ash that we have so much in North Carolina, we are basically contaminating our water resources, and the amount of water that has been degraded because of contamination is really increasing and becoming really significant. Having everything on that, I'm going to introduce our speaker today that's going to address a different aspect of water quality. That would include Emily Bernhardt. She's a James B. Duke Distinguished Professor of Trinity College and Art Sciences at Duke University. Lee Ferguson is Associate Professor of Civil and Environmental Engineering in the Pratt School of Engineering and the Nicholas School of Environment. And Gabby Catul is a Tedros Coyle Distinguished Professor of Hydrology and Micrometeorology at the Pratt School of Engineering, and I have some kind of connection also to the Nicholas School of Environment. With that, I would like to give the torch to Lee Ferguson, and thank you, Lee, for coming here today.
Thank you. So welcome everyone, and I'm going to tell you a bit about the emerging pollutants that we are finding in North Carolina drinking water sources. And so we're going to bring it down pretty tightly to the state of North Carolina and tell you about some of the challenges that we face here. And these are also relevant issues for across the country and across the world. So I'm an environmental chemist, and I spend a lot of time thinking about organic pollutants that enter the aquatic environment. And so if you take a look at sort of this picture on the left, we have a universe of chemicals that we use in consumer products, pesticides, plastics, many different applications, which have a number of different sources and a number of different routes into the aquatic environment. This includes runoff from agriculture, from stormwater. It also includes wastewater from industrial sources as well as human sources. And when those get into the aquatic environment, we can have lots of different things that happen. We can have physical and chemical transformations of these compounds, and then we can have effects of those compounds. And that's the sort of thing that Emily's going to talk to us about later. And these effects can manifest on ecological systems as well as on human systems, and they can pose especially a risk to humans through the drinking water route of exposure. So here in North Carolina, we've been dealing with contamination by a specific class of compounds known as PFAS. And these are per and polyfluorinated alkyl substances that are extremely persistent, and they're called forever chemicals for the reason that they simply don't degrade under natural conditions in the environment. Now, in North Carolina, a few years ago, some colleagues over at EPA and NC State discovered a new class of these chemicals that was occurring in the Cape Fear River. And then subsequent research actually showed that these compounds were accumulating in the drinking water of all of the communities downstream of Fayetteville, North Carolina, that use the Cape Fear River for a drinking water source. And specifically, Wilmington, North Carolina was highlighted. These concentrations were at alarmingly high levels of these compounds, and this led to a fair bit of outcry. It led to regulations by the US EPA and attention by EPA. News articles started to be written about these. Lawsuits were filed against the company that was responsible for these chemicals. And then finally, the legislature, the North Carolina legislature, got involved to try to figure out what to do about these chemicals in the water. So first of all, what are these compounds actually doing in the Cape Fear River? These per and polyfluorinated alkyl substances have been known for quite some time, over 50 years, and they're used in things like Teflon, for example, on Teflon pans. Back in about 2002, the legacy PFAS compounds, such as perfluorooctanoic acid here, were actually replaced by a new generation of these compounds, which are very similar but have subtle structural differences, and this is GenX. They're manufactured right here in North Carolina at a site just south of Fayetteville, and they've been releasing these compounds into the Cape Fear River and contaminating the downstream drinking water for probably greater than 20 years now. So the question that was faced is, how do we avoid this kind of situation in the future, being caught by surprise by these emerging pollutants? And really the only way to do this is to either understand all of the chemicals that are being used in commerce and be able to anticipate their presence in drinking water, or to go out and actually do monitoring, extensive monitoring of drinking water sources for the presence, identity, and the concentrations of these pollutants. So there's some problems with this, though. So that you can ask the question, can we protect water by relying on lists of regulated chemicals that we might know about? So this is a quiz that I give my students in some of my classes, but I think it's instructive. So we can think about our chemical universe. So how many chemicals actually exist? How many chemicals do we know about? This is an alarmingly large number, 80 to 130 million chemical structures that we know about. Now, not all of those are used in commerce, but about 85,000 of those chemicals are actually regulated by the EPA under the Toxic Substances Control Act. Now, of those 85,000, how many have been tested for toxicity? That's probably less than 10,000, certainly less than about 15,000. This is hard to tabulate because it's not well recorded. Now, of those chemicals, how many are actually flagged as priority pollutants under the Clean Water Act? That's only 126 chemicals. And the toxic pollutants of this group are only 65 chemicals. Now, for EPA, how many chemicals has EPA ever banned? Turns out to only be 9 classes of chemicals: PCBs, dioxins, chlorofluorocarbons, asbestos, hexavalent chromium, and a few other compounds. So I think it's clear that we have real challenges relying on these regulated lists to try to anticipate problems in water. So we got into a situation here in North Carolina where academia meets politics. In this case, because of all the attention on the GenX pollution issue in the Cape Fear River, the state General Assembly actually passed a bill that stood up a network of laboratories, including all the major universities across the state, to conduct monitoring of these GenX related compounds like PFAS. I got involved in this back in about 2018 to help spearhead this program for the state of North Carolina, together with some colleagues. So for this work, we've basically gone around to all of the municipal and county drinking water intakes across the entire state of North Carolina, about 400 sampling sites in total, to basically survey the concentration and the occurrence and exposure potential for these PFAS chemicals. And this is the largest monitoring program for emerging contaminants that's ever occurred in the United States. So what did we find? So if you take a look at the summary here, basically this is a plot of all of the sites. This is 376 sites actually that we monitored, with the total concentration of PFAS on the x-axis, ordered in decreasing order. Okay, and so the dotted line, the vertical dotted line here, is actually marking what EPA considers to be a safe long-term drinking water exposure for these chemicals at 70 parts per trillion. And if we zoom in on just the top section of this, you can see that we had about 20 stations that actually had some PFAS concentrations above that dotted line. And so many of these purple or pink lines represent the GenX related chemicals that were in the Cape Fear River downstream of Fayetteville. And some of these concentrations exceed that 70 part per trillion lifetime health advisory level by quite a substantial amount, up to 400 and over 400 parts per trillion. And if you compare this with measurements that have been made across the country at other cities and other municipalities, you can see that the concentrations that we're seeing, around 400 parts per trillion, are well above what's been reported by Environmental Working Group for many of these other areas across the country. And in fact, even in the Environmental Working Group data, North Carolina had actually 2 of the top 5 concentrations for total PFAS in drinking water. So I think it's clear that North Carolina faces some real challenges with respect to these chemicals in the drinking water. And it's not just the Chemours GenX contamination that we're facing actually in the state. Here's an example of a small town called Maysville, North Carolina, in eastern part of the state that relies on a single well for its drinking water. We actually found that when we looked at the PFAS signature in this water, we found signatures that were indicative of firefighting foam contamination, possibly from activities at the nearby fire station. So once we found this, we were able to actually get Maysville switched over to the county water supply and alleviate that contamination. But they're still facing challenges with respect to finding a new well, drilling a new water source. So I'll just close with showing you a map of sort of holistically what we found across the state of North Carolina in terms of PFAS concentration. So this map tells a story. And so Western North Carolina, you see a lot of blue and green spots. Those are low concentrations of PFAS, relatively low. And then in Eastern North Carolina, you also see a lot of blue and green here, punctuated by a few red dots. So this sort of red arc right here down in the southeastern part of the state is the Cape Fear River, and that represents the compounds coming from Fayetteville Works, from Chemours. Here's Maysville, North Carolina, but the rest of eastern North Carolina relies quite a bit on groundwater for its drinking water, and those groundwater sources are relatively clean. If you look at central North Carolina, here in the Triad and the Triangle, now you start to see a lot of yellow and orange and occasionally a red dot. That represents relatively high concentrations of PFAS in the drinking water sources, and it reflects our reliance on surface waters here in central North Carolina for drinking water. And unfortunately, if you're relying on surface water for drinking water, you're almost always downstream of someone else's wastewater. And so this just highlights the need for advanced treatment to get rid of these chemicals. Okay, so that's what I had to tell you today. And for that, I will go ahead and pass the torch over to Professor Bernhardt.
Thanks, Lee. Hi, folks. Thanks for agreeing to spend your afternoon talking about water quality with us. It's a fun opportunity to talk about some things that I both love and am concerned about. So I'm an aquatic ecologist and ecosystem scientist, and I love rivers. I'm showing you a picture here of one of my favorite rivers here in the Duke Forest in North Carolina, which hopefully many of you have seen during your time at Duke. I love rivers not just because they're beautiful to walk beside, but because they're amazing ecosystems that have the power to take light from the sun and the leftovers from the terrestrial ecosystems that surround them and turn them into an incredible diversity of life, things from the charismatic fish and otters and beaver and salamanders to the less charismatic but equally interesting aquatic invertebrates that sit at the base of the food web. And for much of the world, these freshwater food webs are incredibly important sources of protein. And in all of the world, they're incredibly important sources of recreation, sports fishing, et cetera. And today I want to talk about what rivers look like in cities. So most of the people on Earth now live in cities. And that's going to continue to be the case through the projections of population growth over the next century. And so the rivers that most of us now encounter in our daily life are, in fact, urban rivers. And if you look at really any city, you can see that the way that water moves through that landscape and the way that water is going to enter, the chemicals it's going to pick up is going to be really different in a city than in a forest or a prairie system. And this is, well, I'm going to talk about data from here in central North Carolina, but I think you could really apply this to basically anywhere in the world where we make a pavement-intensive city. And so the rivers that most humans are encountering in their daily life, if they're not buried in a pipe, are going to be packed with plastic, trash. They often smell bad. They're often muddy and dirty. And so urban streams don't get a lot of love. And yet, these are the systems that most of our children encounter in their sort of first explorations of an aquatic ecosystem. Rivers are often incredibly important centers of commerce, culture, traditions, rituals. And so we have this really interesting relationship with our urban rivers, right? In that we use them to dispose of waste, as Lee just shared with us, but we also expect them to provide us with all kinds of amenities and services. one of the chief problems of what we do to rivers and urban systems is that we design cities not to flood. And so we create a huge amount of infrastructure to move water off the landscape as fast as possible when it rains. So every stormwater drain that you see on a road is basically hooked into kilometers worth of pipes that are taking any rainwater and moving it really rapidly into a downstream channel. The maps here on the left of this screen are of Goose Creek. It's a small tributary here in the city of Durham that feeds into Ellerby Creek that then goes into Falls Lake, the water supply for the city of Raleigh. And you maybe can see the tiny little bit of blue channel on this map at the top. That's the only part of the stream that's actually out in the open. The rest of the water moves through the system through the black lines, which are stormwater pipes. And so when it rains, all of this watershed is basically moving water directly and very efficiently through pipes into stream channels. And that's really the base of all of the problems that we see with urban streams, because it means water moves really fast. If I now expand out now to the entire city of Durham, shown on the left-hand side here, we've got the entire municipal boundaries of Durham. The blue lines are the open stream networks, and every single red dot is a stormwater drain. So basically you can see that on the right, I'm showing you of that stream channel, how much of it is more than a kilometer away from a stormwater outfall. And the answer is almost none. Less than 0.5% of the entire river network in the city of Durham is more than a kilometer away from a storm drain. So they're all being subjected to urban stormwater. And what does this mean? It means we're routing water really efficiently off pavements and roofs and walkways into river channels, which means that we have really high storm flows. This is just a picture of a stream leading to Duke Forest one day before and the day after a major storm event. That's pretty stressful for the things trying to live in streams. But then perhaps even just as important, that water is bringing with it all kinds of things washed off of urban surfaces. I'll direct you here to the bottom panel in this set of graphs. This is showing you that same Goose Creek, the sort of urban area in central Durham, versus Stony Creek, which is the watershed from the picture I showed you in the very first slide. And when I look at the bottom, that's just a map of the temperature, the surface temperature of those two watersheds on the same day. And you can see that it's much, much hotter in the city than it is in the forest. That's not going to surprise you, but you may not have thought about the fact that when it rains, that heat washes directly into stream channels. So we see that urban streams are hotter all the time. This is across 80 streams here in the triangle. The bottom line is a highly forested stream. The red line highlighted here is an 82% paved watershed. That's about a 5-degree temperature change throughout the summer. And on the right-hand panel, I'm just showing you on a single day when there was a storm event that you can see basically heat pulses coming off of urban pavements of 5 to sometimes even 10 degrees over the course of just a few minutes. So again, thinking about what that means for those living in a stream, organisms living in a stream, this is a pretty stressful kind of environment to live in. Why am I talking about temperature and a conversation about water quality? Well, if you can bring heat, which can dissipate very rapidly in water, if you can bring that heat that effectively into a stream channel, just think what you can do with everything else that washes off roads that's dissolved in water or carried by water. So if you think of basically in an urban setting, every road being a stream channel, a tributary to the rivers in which that we think of as traditional rivers, everything that ends up on a road or a pavement or a roof is going to be washed by that stormwater into stream channels. And this is just an early survey of emerging contaminants in urban systems across the country done by Dana Colpin. And you can see that those urban stormwaters contain tremendous amounts of incredibly wide variety of both traditional chemicals and a number of synthetic and organic chemicals. And so, of course, we tend to see a loss of species in urban streams, really high peak flows, high amounts of contaminants, hot temperatures, all are incredibly stressful for organisms. And so the higher the amount of pavement that you see on this x-axis, the fewer fish species or the fewer insect species we typically see. It's a pretty depressing way of thinking about rivers, and that's what much of the urban river system research looks like. We study a gradient of pavement, as we're looking at here on the left-hand graph, or we look at forested versus urban sites, and we see these big differences. But a couple of years ago, and this basically would suggest that there's nothing we can do. If you put pavement in a watershed, it automatically moves from the situation on the left to the situation on the right. But a couple of years ago, Dean Urban and I, Dean's a professor here in the Nicholas School, started thinking about how much variability there is in the middle of that cloud of points. So I'm taking that same data from that graph and showing you that actually, if you look across the gradient, it, there's a tremendous amount of variation at individual levels of development. So we wanted to think about, well, what controls those really bad and those really good outliers? Are there kinds of development configuration that minimize those impacts? So we did a study of 240 first-order watersheds across the entire triangle within the cities of Chapel Hill, Durham, and Raleigh. And we looked at the sort of really fine-scale resolution of pavement in those watersheds. And so here I'm showing you for those watersheds, the amount of development or the amount of pavement on the x-axis versus road density. And although there's a positive relationship, hopefully you can see there's a tremendous amount of variability. So those two pictures on the right are two different watersheds that are both have 10% of their watershed in pavement, but tremendous variability in the amount of roads and amount of pipes. So you've got 9 times more pipes and roads in the upper figure versus the bottom, although they'd be classified as the same amount of development. And what this means is that when you look at what happens when it rains on these two different watersheds, you get really different responses. In the same storm, you get really high peak flows in the high pipe density, high road density watershed, and much more gradual ones in the less densely connected watershed. And then in the bottom graph, I'm showing you conductivity. This is a measure of the total amount of ions in solution. And you can see that we barely see a blip in terms of the salinity of the water in the low pipe density watershed, and we see a tremendous increase in the high density watershed. If we take that and look at now sensor data for a whole year's worth of data for two watersheds with low road density versus high road density, you can see that in those high road density watersheds on the right, we're having incredible variability in both the salinity and the temperature of water over the course of a year. Think about what that means for something trying to live in that system. And also imagine every time you're seeing high salinity inputs, you're getting large inputs of other things that are collected off of roads and roofs. And so what we found is that while watershed impervious cover doesn't do a whole lot of good in explaining the variability across these watersheds with similar cover, we found that road density and also pipe density, which is highly correlated, can explain almost 90% of the variation that we see in this variability in the chemical constituents in stream water. I think that's really quite useful. We also found that that same variable explained a tremendous amount of the variation in the tissue concentrations of heavy metals that we found in aquatic insects living in streams. This work done by an undergrad honors thesis student here a few years ago. That's really interesting because when we look at water samples or sediment samples, we typically don't see that relationship. And so it's really this loading of stormwater that's a better predictor of animal exposure, and then exposure to the folks that might eat those organisms. And so if I could sort of turn this from the positive message that I see here is that we actually have a lot of new urbanization to go. So this figure here on the left shows projections for urban development up to 2050. There's still a lot of city being built around the world and city expansion happening here in the United States. As we do that, I think it's interesting to think about whether we can design new urban areas differently to live lighter on the land in ways that reduces the speed and the efficiency with which we're routing contaminants into rivers. And then in our established cities where we already have those pavements, are there ways that we can disconnect these pavements from waterways? And so those are questions that we're exploring in my group, and I look forward to answering your questions. But now I will turn it over to a different story from Gabby Catul.
Okay, we'll go ahead and start then. Thank you, everyone. And I'd like to begin by thanking the FOREEVER Learning Institute for hosting this forum. This work is done in collaboration with my graduate student, Pratt. The title of the talk is, in fact, uses a familiar concept of peak oil for grain production sourced from groundwater. Peak oil refers to the point when oil production seizes its upward climb, and then begins to decline. Its roots lies in an empirical bell-looking shaped curve that was proposed in 1956 by a geologist named Marion King Hubbert. Hubbert actually was studying extraction of oil, and he came up with a theory that is empirical, but it seems to have caught on in almost all studies that deal with renewable, non-renewable resources. And this topic, of course, continues to dominate headline news today, as Avner mentioned. So what did Hubbert do? He was studying U.S. crude oil production. And what he found is that in the early phases where you are installing oil wells to pump oil, the production rate is quite low because there aren't too many wells. And then as the profits from oil trickle back into investment in infrastructure to harvest more oil, production goes up until a peak is reached. But once the easy oil has been removed, and all the oil wells begin to dry up, and of course there are less resources to harvest, the oil production starts going down. And what Hubbert did is he made the assumption that if you envision a sort of symmetric shaped looking function to fit the data in terms of oil production, he used a data set from 1860 to 1948 to fit basically US oil production, and was able to project into the future the occurrence of peak oil and the occurrence, the year at which peak oil might happen, which was in the early 1970s. Since then, in fact, the reported US crude oil production followed Hubbert's curve quite accurately until year 2000. In year 2000, there was a technological disruption because of the availability of tight oil and shale oil. So what does that have to do with water and grain? Well, these are some of the questions that we're going to try to answer in the next few minutes based on this background from Hubbert's theory. Can the concept of peak oil be extended to represent depletion of groundwater in regions where replenishment is too slow? Avner already hinted that this is happening in many areas around the globe. Does grain production sourced from groundwater follow a Hubbert-like curve as a non-renewable resource? Can a mathematical framework be derived to link groundwater withdrawals to grain production? And what are its predictions for grain production into the future, very much like Hubbert did for oil? So to answer those, we will first start by defining what groundwater withdrawal is. And that's basically the imbalance between two quantities, the recharge and the withdrawal. So on the left, you find a global map of recharge. These are often reported in volume of water per unit area, per unit time. So they are typically reported in inches per year or millimeters per year. And of course, it's quite variable depending on the patterns of rainfall. The withdrawals, on the other hand, are concentrated in urban areas or where reliance on groundwater is needed, or agricultural areas where irrigation sourced from groundwater is used to produce crops. Now, if we look at the map to the right, there is a focus on 4 key aquifers. Avner already hinted at those, but our focus will be primarily on the High Plains Aquifer in the United States, primarily due to the availability of long-term records from that region. The High Plain regions is an interesting region because the recharge rate is quite dramatic when one looks at the gradient from north to south. In fact, in the northern part of the High Plains Aquifer, you have recharge rates that are on the order of 100 millimeters per year. But as one goes to the south, you find that the recharge rates can drop to 2 millimeters per year, so almost a factor of 10. And so that allows us to study basically groundwater recharge mechanisms across such a large gradient. If also one looks at the water level changes over the last 57 years or so, one finds that in the northern High Plains, there is actually a slight increase in water level, whereas if one goes south, there is a dramatic decrease in water levels over the last 57 years. So clearly the US High Plains Aquifer enables us to look at stresses as one goes from north to south. And for that purpose, we will decompose the northern High Plains, we will decompose the High Plains Aquifer into 3 regions: the northern High Plains, the central High Plains, and the southern High Plains, with Nebraska representing the northern High Plains, Kansas representing the central High Plains, and Texas representing the southern High Plains. Okay, so the mathematical model that we will use to interpret the data from these regions is primarily borrowed from biology. It's a classic predator-prey problem. And the thinking behind it is as follows. One may envision the groundwater as in fact a prey, and basically crop production as a predator. And it is enabled through planting of wells, if you like. So basically we chase the prey by inserting wells and pumping groundwater. So just as predators and prey respond to changes in each other's population, as one might have seen, the mathematical model that is developed here to represent this dynamics between groundwater harvest and grain production allows for feedback between the costs of chasing a shrinking water resource and the profits of agricultural output through irrigation. Overall, the model will produce 2 curves, one for groundwater use over time, which is kind of representing the prey, and the other one, of course, for total crop production over time, which is kind of representing a predator. Both can peak and decline, but there is no guarantee or a priori assumption that they will do so. And I'm happy to answer questions on the mathematical model in the question answer session if there is interest in that. So let's jump right into what the model predicts for the High Plains Aquifer, and we start from the north. So these graphs, there's going to be a sequence of 3 graphs now for each region. On the left, you will see groundwater withdrawals in cubic kilometers per year. On the right will be crop production in tons per year as a function of time. And what you see are model projections basically for groundwater withdrawals that are coupled mathematically to crop data. And the dots are, of course, reported data from these regions. And for Nebraska, given the high recharge rate, there is no issues with groundwater withdrawals yet. There is no peak water or peak grain for that matter. In fact, the projections is that crop production will continue to climb up to year 2050 without much impediments from water. If we go to Kansas, there is more exciting dynamics happening there. We see that already Kansas experienced a peak water, very much like peak oil, with a difference. The peak water that has emerged in Kansas is asymmetric, unlike what Hubbert assumes. And that's partly due to the fact that there's a finite recharge. What is more interesting is the fact that peak grain occurred some 17 years after peak water, and it also follows a symmetric shape curve. And it is peaking right now. So in other words, we're beginning to see the plateau in 2020 to 2022 with the projections of the model that there will be a decline in grain production in Kansas. Texas perhaps has the most exciting dynamics that one can envision from a mathematical model. In the early phases of groundwater withdrawals to produce crops, Texas was almost following a textbook example of a Hubbert curve. Its groundwater withdrawals were symmetric. There was a peak followed by a rapid decline, and then there was a lag between crop production and water harvesting, with a 7-year difference between the two, meaning that basically the crop production cycle and the groundwater withdrawals were tightly coupled together. But in the 1990s, something interesting happened. There was a rebound, in fact, in groundwater withdrawals, followed by another rebound in crop production. And that's exactly a technological disruption. Again, just like has happened in oil, farmers in Texas, in fact, adopted very efficient irrigation practices, referred to often as low energy precision application, or LEPA. And that happened pretty fast. Within 10 years, almost all the farmers in Texas have adopted this sort of irrigation practices. And interesting enough, that allowed a peak water to re-emerge again, followed by a peak grain, with the finding that there is more water, but there is less water that is needed now to support a higher crop production. But nonetheless, this doesn't solve the original problem, which Avner alluded to. In fact, that only just allowed this peak to occur, and then we're again almost following a classic textbook of a Hubbert curve, where you have almost symmetric shape in groundwater withdrawals as a function of time and crop production as a function of time. Okay, so what about projections? Again, comparing these 3 states, we look at 1980, we find that Texas, Kansas, and Nebraska had about the same groundwater-based crop production in tons per year. By 2016, we find that both Texas and Kansas went up a little bit, but Nebraska dramatically increased. However, the projection from the model is that by 2050, we will have a mild reduction in Texas, a mild reduction in Kansas relative to our 2016, yet Nebraska will continue to climb up unless there is another technological disruption, so to speak. Looking forward into the future, and this is the last slide, again, on a more positive note, there is now technological innovations that are happening in the remote sensing that are enabling us to monitor basically groundwater resources in ways that we have never had before. The GRACE satellite, this is the Gravity Recovery and Climate Experiment, is able to model minute fluctuations in the gravitational field of Earth that can then be linked to massive withdrawals or massive changes in water levels on the Earth's surface. And those are very coarse-grained data, but they're consistent and they're around the globe. The other big technological innovation that has happened is the release of MODIS data, Moderate Resolution Imaging Spectroradiometer, and that is able to monitor changes in leaf area index as a function of time across the globe. And if that can be correlated somehow to grain production, then we have all the necessary ingredients to begin to talk about forecasting basically peak water and peak grain across the major aquifers. And with that, I will stop. Thank you for your attention.
Thank you very much for all the speakers. it's grateful to have this very wide range of expertise in this short time of presentation. Some questions have already been addressed by Emily, but I kind of open for our guests to present some questions, either on the chat or directly if they want to speak up.
Is it okay if I ask a question?
Sure, of course.
Yeah. So, Lee, what are the thoughts on cleanup of PFAS? How persistent is it? Does it eventually get sequestered somewhere?
Yeah, those are great questions, Emily. So cleanup, this is something that there's a lot of attention being paid to right now in drinking water utilities across the globe. So there's a couple of options. The most effective technique is reverse osmosis. But it's very difficult and very energy intensive to do on a large scale. So Brunswick County down near Wilmington has actually just, I think they're almost finished building a large scale reverse osmosis plant to deal with this. The other technology that's often used is sorption, so activated carbon treatment, similar to what's in your Brita filter at home, but on a much larger scale in a utility. The problem with that is that many of these compounds like GenX don't typically absorb very strongly to the activated carbon, and it has to be regenerated pretty quickly, pretty often. So there's a lot of challenges with trying to treat drinking water sources. The better way is to try to eliminate them at the source. In terms of where they end up ultimately in the environment, so they're quite water soluble, and so they do hang out in the water column. Some of them will adsorb to sediments. Some of these compounds will also bioaccumulate. They don't undergo any appreciable environmental degradation. So they will be in the environment for as long as they are basically not buried in sediment, essentially.
Okay, so we have some flow of questions. Perhaps I'll do it by order. Maybe the first one is for Gabby. The entire Western US is under drought kind of condition. How this you projected to be affecting agriculture?
I'm going to go ahead and share my screen because I think it'll be easier to point out to certain terms in the equation. So apologies for that, but I think it's easier. Let me see. So basically, climate change has several impacts on the recharge of the aquifer. Of course, that becomes important. So these are two equations. One representing the accessible groundwater, which we have called the prey. It interacts with grain production, the predator, through this term. Then there is a source of water that comes from the recharge itself. And then, of course, if you are drilling more wells, you will expand the area of groundwater extraction. So that is also a source. In terms of grain production, of course, there is you gain when you interact with groundwater. So that's a source here. But there is, of course, a depreciation term that is the same. So at least in the simplified model, the recharge of aquifer area is dependent on rainfall, and that is going to be impacted by climate change. And of course, the economics that drive that is going to be impacted by climate change. And it depends how much future extraction of groundwater is going to be needed in certain areas. And the reason I put this is that if one goes to, in fact, the harvested dedicated acreages in each of these regions, we find that in Nebraska or the northern high plains, the harvested irrigated acreage is still growing. So basically, even if there is climate change, there is capacity to still drill more wells, and that seems to be happening. If one looks in Kansas and Texas, there is none. Basically, the area that can be used to extract groundwater has already been used, and it's perhaps even shrinking a little bit. So basically, Nebraska can offer a little bit of a mitigation by allowing more groundwater to be harvested. How long this is going to be sustained? At least for 2050, it looks it is doable. So that's basically where we are. But you are right. The droughts will also require more irrigation water, and hence the extraction rate will be increasing.
If I may to add that, there is the water quality component on the impact of drought on water resources. We have seen in many parts of the world that climate, and that's also related to the general question about how climate change affect water availability and water quality, in addition to the decrease of precipitation and recharge and runoff that we see in surface water and groundwater. We see a continued degradation of water quality, of groundwater quality associated with climate change, with an increasing rate of salinization of groundwater. And also we see some cases where we see a drawdown of the groundwater table. It changed the water chemistry and allows some chemicals under what we call oxidizing condition to becoming more prevalent in the water, like hexavalent and chromium, for example. And therefore, water quality is kind of another kind of a hidden component that would make water, even if we have water, make them unavailable for consumption. And that's something, for example, in India, we are facing a major crisis, not only because of we don't have enough water to supply the increasing population, but the water that is being supplied is actually inadequate for human consumption and for agriculture consumption as well, in places like Rajasthan and Punjab, where the major agriculture takes place. So it's going to be pretty challenging into the future to generate enough food to have enough clean drinking water. Going to some more question. Maybe I'm trying to keep the order for Lee. What timeline you see for mitigation impact for the recent legislative and regulatory change for PFAS in North Carolina?
Yeah, so there's a number of aspects to that. So right now, we still don't have regulations here in North Carolina or actually nationwide for PFAS. There's simply health advisory levels, which are not enforceable. However, EPA has declared their intent to establish a water quality criterion for PFAS, for some PFAS in the coming months. Once that happens, I think we'll see quite a change in at least the levels of PFAS that are released. Now, that said, the regulations, we're actually seeing change even before the regulations hit, and that is because of the bright light that's being shown on this issue by both the scientific community as well as frankly, the news media and the US EPA. So what we're starting to see is that the large point sources, such as the Comores facility, military bases that use large amounts of firefighting foam, those facilities are starting to take action themselves to try to shield themselves from liability once the regulations come into place. The real problem is going to be once those large point sources are removed, it's very hard to remove the diffuse sources of PFAS that come from our use of these materials in consumer products. So landfills, disposal of these materials in landfills, so the leachates that come from that, as well as simply the use of these materials and the discharge of those wastes into wastewater. Wastewater treatment plants in general are poorly equipped to remove PFAS, and it would take quite a large investment to upgrade all wastewater treatment plants across the country to meet the discharge criteria that would be necessary to remove these below, let's say, 10 part per trillion in water. So I think what we're going to see is a sharp decline in the concentrations of most PFAS in point sources, but sort of a very slow tail that represents our use of these materials just in our consumer culture.
Question for Gabby. Could you speak to see Grace and Morris being used in the future? The question are testing with them and all that.
Thanks, that's a great question. In fact, the reason for thinking about a model like this is that the original intent was to come up with something that epidemiologists have done way back, which is called the basic reproduction number. For deciding on whether you have a pandemic or not. And so the thinking was to derive something similar to that from this system and use precisely Grace and MODIS for assessing how far we are off from having a switch in the basic reproduction number for the food-water nexus to go from a major disaster to being sustainable. And that's basically what we are thinking of, is how do we combine these models with data that would be coming online from Grace and Modis to answer those questions, whether we are going to be in a basic reproduction number analog that is bigger than 1 or less than 1 for sustainability.
To Emily, to design more sustainable urban areas, should we expect surface storage pond on whose property, filtration facilities, permeable pavements, and go on? So you see the question.
Yeah, and I was just responding to Barry in the chat. Good question, and I'm going to take that one and the question below from Renee Brown, which is about new development. But I think it's all of the above, right? It's no single solution is going to get us there. It's trying to find basically any way that you can slow the connection between rainwater and an urban stream. You're going to have benefits from that. And so it's sort of all of the above. And then when you're thinking about new development, I think that's where it's really interesting. My dream and the dream of many folks like me who study this problem would be to find developers that are actually interested in having researchers come in and study development as they go in. But I think the idea that low density development, like your classic suburbia with cul-de-sacs, is low intensity is actually not true, because it requires a huge amount of road connections to actually have that kind of low density housing. So if we can think about creating the same amount of housing, but requiring less creation of roads, that's a way of thinking that's a little bit different. And I don't know if you're asking the question, I think an important thing to think about, a lot of what we do to protect water quality in cities is to establish riparian buffers or streamside forests. But the fact that all the water goes through those buffers and pipes means that they have virtually no impact on water quality. And so we really have to think beyond what's happening on the surface. We have to think about the conveyances, which are the roads and the pipes that are moving this water through, and make less of them and make them sort of less efficient at moving water really rapidly from pavement to stream.
Thanks, everybody. Our wonderful speakers, Emily, Gabby, and Lee. That was truly fascinating and a lot of great information. So we really appreciate it.